Hello dear students. So we had already done the first unit of your abstract algebra course, and in the last lecture I had given some introduction to the second unit, where I started with order of a group. Okay, well, that is the number of elements of a finite group. It is called order of a group. Then we have this notation that a to the power n, this is actually equal to a star. A star means you are operating a n times. Okay, n times it is being operated on itself. Okay, so that is denoted by a to the power n, right? Next we have seen that a to the power n star with a to the power m, this is same as a to the power n plus m. Okay, so this actually follows from the associative property, right? And a to the power n whole to the power m, this is the same as a to the power n into m. Okay, so since we have the inverse notation also, so if n is negative, if n is negative integer, right, negative, then a to the power n is actually represents a to the power mod n inverse. Okay, inverse of this a to the power mod n, right? Say a to the power minus 3, what does it represent? It will represent a to the power 3 whole inverse. Okay, so it actually represents a star a star a, okay, then taken inverse, right, like that. So for negative integers also we have this notation, right? So if n is positive, of course this notation is for n positive. Okay, n greater than 0 and n belongs to z. Okay, for n equal to 0, your a to the power n is actually identity element, and for n negative, if n is negative, a to the power n is a to the power mod n whole inverse. Okay, inverse of this. We know how to compute a to the power mod n, because a to the power mod n is just a star a star a star, like that, taken mod n times. Okay, so we know how to compute that. So this is the notation we will be using. So using this notation, we have something called order of an element of a group. Order of an element of a group. Okay. So what is that? The definition is the order of an element say A in a group G is the smallest positive integer such that smallest positive integer n, okay, n, such that a to the power n is equal to the identity element. Okay, e, where e is the identity in G. In G. Okay. Right. If no such element or no such positive integers exist, if no such positive integer exists, then we say that A is of infinite order. Infinite order. Okay. So yeah, so the order of an element is denoted by mod G. Okay, right? So it's not necessary that in a group always you will be able to find an integer n, positive integer n, such that a to the power n equal to e. Okay, so in particular for the 0 means identity element itself. Okay, sorry, for the identity element we can always find e to the power 1 is equal to e. So identity element here in a group has got order 1, right? For identity element it's okay, but the others there might be some other elements which do not have a finite order. Okay, say for example, let us see some example, then we'll understand. For example, consider the group. Say we start with this very simple finite group 1 omega square, this of cube roots of unity. We have already seen that it's a group roots of unity with respect to multiplication. Okay, it's a group with respect to multiplication. Then order of 1 is 1 only. Okay, as 1 to the power 1 is equal to 1, right? Order of omega is 3, as omega to the power 3 equal to 1. Okay, omega cube is 1. Now omega is not equal to 1. Omega square is also not equal to 1. Okay, omega is actually minus 1 plus I root 3 by 2. Okay, omega square is minus 1 minus I root 3 by 2. Okay, so omega is not equal to 1. Omega square is also not equal to 1, but omega cube is 1. Okay, because these are the cube roots of unity. If we take cube, it satisfies omega cube equal to 1. Okay, so order of omega is 3. Okay, as omega cube is equal to 1. What is the order of omega square? So here you see omega cube is 1. Also omega to the power 6 is also 1. Okay, because omega to the power 6 can be written as omega cube whole square. So that is also 1. But 6 is not the order. Okay, because what is the definition? Definition of order says that it is the smallest positive integer n which satisfies a to the power n equal to identity. Okay, so not only a to the power n has to be identity, this n has to be the smallest of all possible such possibilities. Okay, say here if we have omega to the power 12 is also identity. Okay, omega cube whole to the power 4, so that is also 1, but we will not say that 12 is the order of omega. Okay, because there are other elements which are lesser than 12, so this order of omega is 3. Similarly, omega order of omega square is also 3. Okay, as omega square is not equal to 1, omega square whole square, this is equal to omega to the power 4, which is actually omega cube into omega, so that is omega, so which is also not equal to 1, but omega square whole cube, this is actually omega cube whole square. Omega cube whole square is 1 square, that is 1. Okay, so order of omega square is 3, right? So order of 1 is 1, order of omega is 3, order of omega square is 3. So for this particular group we have done. Okay, similarly next you consider this, the group, say G equal to 1 minus 1 I minus I. Okay, so these are the group G of consider the group G equal to this of fourth roots of unity. Okay, fourth roots of unity, right? Then with respect to multiplication. Okay, with respect to multiplication. Okay. Then we have order of 1 is equal to 1 only. Okay, that's 1 is the identity element. Okay, order of minus 1 is actually equal to 2, as minus 1 whole square, this is equal to 1, right? Then order of I is what? Order of I is actually 4, as I to the power 4 equal to 1. Okay, anything with lesser power is not equal to 1. Okay, I not equal to 1. I square is minus 1, which is not equal to 1. I cube is actually minus I, which is also not equal to 1. But I to the power 4 is 1. I to the power 4 is actually I square whole square. So this is minus 1 square. This is 1. So 4 is the least positive integer which satisfies this. Right? So order of I equal to 4. Similarly, order of minus I, that is also 4. Okay, right? So this group has elements of order 1, 2 and 4. Okay, next, say you consider the group Zn. Say I write something like Z5, which is equal to 0, 1, 2, 3, 4. Okay, with respect to addition modulo 5. Okay, then what are the orders? Okay, order of 0 is equal to 1. Okay, because 0 to the power 1. Okay, so here actually the operation is additive. So instead of writing 0 to the power 1, we actually write 1, 1, 0. Okay, 1, 0 is equal to what? This is equal to 0, right? So means 0 added to itself. Okay, means not added, actually 0 is just 0. So actually we are taking only 1 0. So that is what. So this is the thing. Order of 0 is 1. So 0 is the identity. So that is right. 0 is identity element, as 0 is identity. Okay. So order of identity is always 1. Okay, because identity itself satisfies e to the power 1 equal to e. Okay. Then order of 1. Okay, what is the order of 1? So let us try. So we have to find how many times 1 has to be operated on itself to get 0. Okay, so if we operate 1 plus 5 twice, okay, so this is something like 2 into 1. Okay, so let us stick to this notation, 1 square only. So here 1 square is actually 1 plus 5. Okay, 1 plus 1 modulo 5, so that is actually 2. So which is not equal to 1. Then 1 cube, let us try. 1 cube is 1 plus modulo 5 plus another modulo 5. Okay, because of associative operation we can just add them together. So 1 plus 1 is 2 plus modulo 5 is 1, so this is 3. Okay, this is actually 3. 1 cube is 3. Similarly 1 to the power 4 is 4. Okay, and 1 to the power 5, if I just do it, 1 to the power 5 is 1 to the power 4 plus modulo 5 of 1. Okay, so this is 1 to the power 5 is 1 to the power 4 is already 4 plus modulo plus 1 modulo 5. So 4 plus 1 modulo 5 is actually 5 modulo 5, right? So this is actually 5 mod 5. 5 mod 5 means actually 0. Okay, if we divide 5 by 5, the remainder is 0. So we get 1 to the power 5 is equal to 0. So here the order of 1 is actually 5, as 1 to the power 5 is will give you 0, right? So let us check what are the orders of the other elements here. What is the order of 2? So 2 added how many times will give you 0. So order of 2 is equal to what? See, what I have to do is means under what condition this sum a plus b will be 0. This will be equal to 0 if a plus b is divisible by 5. Okay, only then it is 0, otherwise it's not 0. Because the division is means this operation itself is defined that way. A plus b modulo 5 is actually the remainder when a plus b is divided by 5. Okay, so if I want that the sum has to be 0, then the sum of these two should be divisible by 5, right? If there are 3, then the sum of these 3 should be divisible by 5. Okay, so if I want to find out the order of 2, what I have to do? I have to find that how many 2's added together will give you a multiple of 5. Okay, so that after dividing by 5 or taking mod 5, we get the remainder to be 0, right? So here 2 it can be added to itself 5 times. Okay, 2 plus this is 2 to the power 5, this is equal to 0. Okay, what is 2 to the power 5? 2 to the power 5 is actually so actually 2 to the power 5 is actually 2 plus 2 plus modulo 5 2 plus modulo 5 2 plus modulo 5 2. Okay, so there are 5. So 2 plus 2 is 4. So I can add this 2 together. 4 plus modulo 5 of 2 plus the last 2 I add together. So it's 4 modulo 5. Okay, so 4 plus 2 is 6. 6 mod 5 plus 4 mod 5. Okay, so the 6 mod 5 is actually 1. So 1 plus modulo 5 4. So it's 5 mod 5. So what is 5 mod 5? 5 mod 5 is actually 0, right? So 2 to the power 5 is 0. So order of 2 is also 5 here, right? What is the order of 3? Order of 3. So that is also equal to 5, right? 3 plus 3 is 6. It's not divisible by not divisible by 5, right? If you add another 3, so this will be equal to 9. This is also not divisible. If you add another 3, this will be 12. That is also not divisible. But if you add another 3, now you will get 15, which is divisible. So this is congruent to 0. Okay, mod 5. So order of 3 is also 5. And order of 4, that is also 5. Okay, so these are the orders. 1, 2, 3, 4, 5. Okay, so we have done the orders of this type of elements. Another one, let us see. Let's consider UN. So the groups that we had already done, right? So consider UN. Say U10. Okay, U10, which is equal to 1. The next one is 3. Then the next one is 7, 9. Okay, 1, 3, 7, 9 of positive integers less than n, less than 10, and relatively prime to 10. Okay, to 10. Then U10 is a group. With respect to multiplication modulo 10. Okay, with respect to this operation, it's a group. Now let us see whether we can find out the orders of this its elements. Okay, so in U10, order of 1 is 1. Okay, order of 1 is equal to 1. So 1 is the identity. Okay? 1 is the identity. So identity element here is always of order 1. Then order of 3. Okay, so let us try to find out what is order of 3. So what is 3 into 3? You see, it's 9 mod 10. Okay, so 9 mod 10 is actually 9 only. So 3 into 3 is 9. Okay, so can we just guess something? That how many 3's has to be multiplied so that the product that we get when divided by 10 gives you remainder 1. Okay, so if you just read the tables of 3, or means not the tables, the powers of 3. 3 square is 9. Okay, 3 cube is 27. Okay, so I mean you don't have to do this calculations step by step. Okay, so in the rough you just think about this 3 square, 3 cube. So this 3 square is 9. This, if you take mod 10, this is congruent to 9 only. Okay, this is congruent to 9 mod 10, right? 3 cube is 27. This is congruent to 7 mod 10. If you divide 27 by 10, then the remainder is 7. 3 to the power 4 is actually 81. So here you see, if you divide 81 by 10, then the remainder is 1. Okay, so we have got that this 4 is the least positive integer which satisfies. 3 to the power 4 is same as the identity. Okay, so 3 into 3 into 3 into 3. If we take 4 times, so this is actually equal to 81 mod 10. So this is same as 1 mod 10. Okay, so therefore 3 to the power 4 is equal to 1 here in this group. So order of 3 is 4. Okay. So 3 is a order 4 element. Okay. Then let us see whether we can find out the order of 7. So for 7, what do you see? 7 square is 49. Okay, so if we divide by 10, the remainder is not 1. Okay, 7 cube is 343. If you divide by 10, its remainder is 3. Okay, this is congruent to 3 modulo 10. Okay, what about 7 to the power 4? 7 to the power 4, see, we don't have to multiply with 343. We can just use the fact that 7 to the power 4 can be written as 7 cube into 7. And 7 cube is already congruent to 3 modulo 10. Okay, so this is ultimately congruent to 3 into 7 modulo 10. So that is actually congruent to 21 mod 10. And 21 when divided by 10, the remainder is 1. Okay, so here also the order of 7 is equal to 4. Okay, what about 9? What is the order of 9? So you see 9 squared is 81, and this is congruent to 1 mod 7. Okay, so in this group 9 squared is 1. Okay, so in U10, 9 square, which is equal to 9 into 9 mod 10, so this is equal to 1. Okay, so order of 9 is actually 2. 9 equal to 2. Okay, so that way we can find out the order of elements of a group. But interestingly, you see, if I consider z with addition, okay, ordinary addition, the set of integers with respect to ordinary addition. Okay, if I consider this group, okay, then order of so what is the identity element here? Identity is 0. Okay, additive identity here is 0. Order of 0 is 1. Okay, this is correct, but we cannot find out orders of other elements. Okay, so suppose I want to find out the order of 1. So see, 1 plus 1, this is 2, right? 1 plus 1 plus 1 means 1 square. If I write it this way, 1 cube, this is, so here see, this 1 square is not 1 into 1, because here our operation is plus. Okay, so this 1 square, when we write for the group Z plus, this actually means 1 plus 1. Okay, so it's 2. 1 cube is 3. Okay, 1 to the power 4 is 4. Okay, so that way 1 to the power n is equal to 1 plus 1 plus dot 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 up to 1 added n times. Okay, so this gives you exactly n. Okay, so for n belongs to natural number, so which is non-zero. So we cannot find out the order of 1. Means the element 1 doesn't have any finite order. So 1 is of infinite order. Before that I can write, so there doesn't exist. So whatever natural number you take, 1 to the power n is always going to be n. Okay, so there does not exist any natural number or positive integer n such that 1 to the power n equal to 0. Okay, so therefore this 1 is of infinite order. We cannot find an n such that 1 to the power n is equal to identity. So similarly 2 is also infinite order. Any other elements here in Z is of infinite order. Okay, the only element of finite order is 0 itself. Okay, the identity element itself. Okay, so you see there are many groups where elements may not have finite order. Okay, so we may note it down somewhere. Thus there are groups where elements may not have finite orders. Okay. May not have finite orders. Finite order. Okay. So for example, z plus, no? Z with respect to addition. Okay, simplest group. So here the non-zero elements do not have. So for example, in this, the non-zero elements, non-zero integers do not have order. Okay, or non-zero integers are of infinite order. Infinite order. Okay. So that is the thing. Okay, so let us try to see a few more examples where the elements may have infinite order. Okay, so that is you can take R, set of real numbers with respect to addition. So there also the elements or the real numbers do not add up to 0. Okay, right. Means if you keep on adding real numbers with itself, okay, if it is a non-zero real number, then it will just keep on increasing or decreasing, means increasing in its absolute value. Okay, so it will never be equal to 0. So in R plus also, the element 0, okay, the element 0 is of finite order, but every other element is of infinite order. Is of finite order, but every other element is of infinite order. Element is of infinite order. Right. So this one. What about the set this GLNR that we have done? Okay. What about this set GLNR? Can you find out orders of some elements of this group? Okay. So here also there are certain restrictions. If you have a matrix, say let us consider GL2R. Okay, so if you have a matrix A inside this GL2R such that A to the power n equal to identity element, okay, then this least positive such n is said to be order. Okay, so once it's the definition is obviously the same definition for order of an element. Okay, so here can you think of some? So of course the order of the identity element is 1 only, because this to the power 1 is this identity. Okay, so can we think of some other matrices which have orders greater than 1? Can you think of some matrices which have order greater than 1? So what about this? If you try to see it nicely, -1 0 0 -1, if you multiply it with itself, okay, then what you get? -1 into -1 is +1, then 0 into 0 is 0, -1 into 0 is 0, and 0 into -1 is 0. Okay, then the second row first column, 0 into -1 0, -1 into 0 is 0, and second row second column, so 0 into 0 is 0, and -1 into -1 is 1. Okay, so it's identity. So here the order of this order of -1 0 0 -1, this is actually 2. Okay, so this is an order 2 element in this set. Okay, right. Then you may find some other elements which have different orders. Okay, so that way we can compute what are the orders of various elements, right? So in GLNR there exist certain elements which have finite orders. Okay, right. So next is we need something called the definition of a subgroup in order to understand the further things. Okay, so what is a subgroup? Subgroup of a group. So from the name itself, it appears that subgroup of a group, first it has to be a subset of the original group, okay, and then with respect to the same operation it also has to be a group, okay. So that is the definition. If a subset H of a group itself is itself a group under the operation of G, then we say that H is a subgroup of G. So if a subset H of a group G is itself a group, okay, itself a group with respect to the same operation as in G, same operation as in G, then H is called a subgroup of G, a subgroup of G. Sorry, H is called a subgroup of G, right? If a subset H of a group G is itself a group with respect to the same operation as in G, then we say that H is a subgroup of G, okay. So we will try to see some examples. So there is a notation, it is denoted as H is a subgroup of G, okay. Less than or equal to symbol is also there, yeah, less than or equal to G. H less than or equal to G, this means H is a subgroup of G, okay. So if a smaller set, if you have a set and then if you take a smaller set which also satisfies all the properties of groups, then we can say that it's a subgroup, okay. Say for example, this, consider G equal to 1 omega square, okay, omega square with respect to multiplication. So can you find a smaller or can you find a subset of G which satisfies all the properties of group, okay. So here you take if I take this the element, so this is a 3 element set, so the subsets that we take will be either 2 element or 1 element. If we take the empty set, it's not going to be a subgroup. Why? If so from this definition, is it clear that H is non-empty? From the definition itself, is it clear that H is non-empty? Right? It is clear actually, because H is itself a group, and by the definition of a group, the group is a non-empty set, okay. So H, any subgroup of G will be actually a non-empty set, okay. Empty set cannot be a subgroup, right, because it will not have identity element. One of the main criterion for being a group is that it should have at least the identity element, okay. So here if I take H equal to 1 comma omega, is it a subgroup? Is it a subgroup? So remember, the operation has to be the same, the multiplication operation, okay. So is this a subgroup? So that means basically I have to check whether it is a group or not. So for being a group, first closure property has to be satisfied. The closure property here, what is the closure property? The product of any two elements should be an element inside H only. So here 2 elements are there, so let us see the product. So 1 into 1 is 1, this is in H, but omega into omega, this is actually omega square, this is not in H, okay. So it's not a subgroup. This set H is not a subgroup, okay. But if I consider something like K equal to singleton 1, only singleton 1, okay, then K is a subgroup actually. K is a subgroup, right, because the element 1 multiplied with 1, this is inside K, okay. This is the only one thing we have to check, because 1 has only, the set K has only one element, okay. So to check the closure property, it is just sufficient to check whether the product of 1 with itself is inside K or not, okay. So product of 1 with 1 is 1 only, right. So this is 1 which belongs to K, right. And the other thing, associativity will be satisfied, because associativity of real numbers is, or complex numbers are associative. Multiplication of complex numbers are associative. Then identity, 1 is the identity here, right? And inverse of 1, what is the inverse of 1? Inverse of 1 is 1 itself. Okay, inverse of an identity is identity, right? Inverse is same as identity. Okay, so so here for this set 1 omega omega squared, h equal to singleton 1 or k equal to singleton 1 is a subgroup. Okay, so singleton 1 is a, or I'll write a subgroup of G. Okay, let us see another example. Say G is equal to 1 minus 1 I minus I. Okay, 1 minus 1 I minus I with respect to multiplication of complex numbers. Okay, multiplication. So whether it is a group or yeah, it's a group. So now let us find out some subgroups. Obviously h equal to singleton 1 is a subgroup. Okay, this is the trivial subgroup. So this is actually called the trivial subgroup. Trivial means only the identity element. Okay, trivial subgroup. Identity multiplied with identity is identity only. Identity inverse is also identity. Okay, so if a set has only identity element, it's actually a group. Okay, it actually forms a group. And k equal to, if I take 1 minus 1, okay, then this is a subgroup. If you just observe carefully, this is a subgroup. Why? 1 into 1 is 1, so it belongs to k. 1 into minus 1 is minus 1, this also belongs to k. And minus 1 into minus 1, this is also 1, so this also belongs to k. Okay, so in short, actually I have done the composition table here, right? So k equal to 1 minus 1 is a subgroup. Okay, of course we have just proved the VA, that is called closure property. We need the other properties as well, but associativity is true because it's a subset of 1 minus 1 I minus I. Okay, and this existence of identity, 1 is the identity. Existence of inverse of 1 is 1, inverse of minus 1 is minus 1 only. Okay, so it satisfies all criterion of being a group. Okay, so this 1 minus 1 is also a subgroup. So this particular set has got two subgroups. One is singleton 1, another is the set of 1 comma minus 1. Okay, so that is also a subgroup. But you see the set I 1 comma I, it's not a subgroup. Okay, because 1 into I into I is I square, which is minus 1, which is outside. Okay, so this is not a subgroup. 1 comma I, this is not a subgroup, right? And similarly something like 1 comma minus I, this is also not a subgroup. Okay, because minus 1 whole square, this is actually minus 1. Minus I whole square is minus I. Minus I whole square is actually minus 1. So which is not inside this particular set. Okay, so the only subgroups of this 1 minus 1 I minus I are singleton 1 and 1 comma minus 1. Okay, they are the subgroups, right? Okay, then so in the next lecture we will see what are the properties a non-empty subset should satisfy so that it becomes a subgroup. Okay, bye.